speak about SDP methods. So take it away.
Yeah, can you hear me now, Robert? Okay, perfect. Okay, yeah. Yeah, thanks, Susanna, Robert, and Tony for organizing this great workshop and inviting me. So I want to tell you a little bit about, the problem of refuting constraint satisfaction problems like KSAT, that is, finding short, efficiently verifiable proofs of unsatisfiability. And, what I want to mostly do is maybe slightly against the theme of the workshop, tell you about upper bounds, like how to find proofs instead of like how to prove that proofs don't exist. And, I'll focus on maybe 3 different kinds of techniques that people developed over like, past 2 or 3 decades. And, some interconnections that, were discovered recently between them. Okay. So even though the tutorially part of this talk, that is like, all the math that I'll do actually is really like old stuff, like none of this would be recent. The insights that, I'm basing this talk on are based on, joint works with a couple of students at CMU, Jackson Abaskal and Peter Manohar, and my colleague Venkat Guruswamy. Okay, so let me, start by telling you the algorithmic problem that I am interested in. Now, I kind of think that most of you might actually be aware of this. So think of this mostly as, me setting notation that I will use throughout the talk. So, I'm looking for an refutation algorithm. And so this algorithm, simply takes an instance of a constraint satisfaction problem. And I'm going to think of KSAT as my running example throughout this talk. So, it takes a KSAT formula. The formula will always be in n variables and m clauses. Okay. And the goal of the algorithm is to compute some number v between 0 and 1 with the property that v is an upper bound on the value of v. And value, by value, I simply mean, the maximum possible fraction of constraints that can be satisfied by any assignment. Okay. Now, if, the algorithm computes a value v for a certain formula, which happens to be strictly less than 1, then it, weakly refutes the formula in the sense that, it gives a proof that the formula is unsatisfiable. The weak part is that, in this case, the algorithm is simply saying that every assignment must somehow violate at least one clause. But, I'm also going to be interested in a stronger notion of refutation, which I'm going to call, well, strong refutation. And that simply means that, I would go ahead and certify a bound which is bounded away from 1 by a fixed constant like delta. And, you can think of this as saying that, we are certifying that every assignment should not just violate 1, but, a fixed constant fraction of the clauses. Okay, good. So, solving KSAT or proving unsatisfiability of KSAT is a hard problem. We don't actually expect efficient algorithms for all instances. And so, my goal would be to, find algorithms that work for the largest possible family of instances. And so, specifically in this talk, I'm going to look at 2, different families of random instances, one more general than the other. The first is, the random KSAT family, which, maybe most of you are aware of, or at least, is very, very well studied. What this means is that, I'm going to generate a random, like I'm going to generate a formula phi by simply, taking a random k-tuple of variables and then like randomly negating them uniformly at random. Okay. So in particular, both the clause structure or the hypergraph and the literal patterns are, random in this family. I'm also going to look at the semi-random setting, which is, where the clause structure is worst case. So the k-tuples that appear in the formula are, completely arbitrary, but the literal patterns are still uniformly at random. Now, really strictly speaking, whatever I say also applies to a even more general version of semi-random formulas called smooth formulas. But, in the interest of simplicity, I'll just restrict it to these 2 models today. Okay. All right. So what do I want to tell you today? Well, in some sense, this is the main message of the talk. I'll tell you the story of random KSAT and, what people thought about it and how we proved and how we made progress. And then in some sense, how things generalize and new things come out if you simply find the right proof for, the random case. So, for each of the results, I'll tell you, I'll show you how, just thinking about the proof a little bit differently and try to find somehow the simplest possible proof leads to, newer, cooler results. Okay. So, yeah, let me start with like the story of random KSAT. So, this is an extremely well-studied problem. If you, take an instance with, let's say, some big constant times n clauses, this constant can depend on k, but I'm going to ignore such constants in this talk. Then it turns out that, the formula is unsatisfiable with high probability. So the task of refutation at least makes sense. And, people for a long time have, studied the question of whether there are short proofs, that can prove to us that these formulas are unsatisfiable. And this, was begun in this really a cool paper of Chvátal and Szemerédi, like from 1988. And, there were lots of influential follow-ups, including, some famous papers of Tony, that eventually told us that, there are no polynomial-sized refutation proofs if the number of clauses is, much smaller than, let's say, n to the k over 2. Okay, so when you think of k as always a number bigger than or equal to 3, so n to the k over 2 is, in some sense, at least square root of n multiplicatively away from, this, in some sense, the true bound of n at which formula should be unsatisfiable. A similar line of work, exists on the question of finding semi-algebraic proofs. And they're also, in the, at least in the strongest proof system, which, goes by the name of sum of squares or positive Selenzar's proof system, Grigoriev began the task of proving lower bounds. And we actually know a lot. We kind of know, in some sense, sharp lower bounds for all CSPs, thanks to some papers, a few years ago. But for this talk, as I said, mostly my interest is in upper bounds. So I'm simply going to summarize the statements that I told you as saying that, lower bounds rule out polynomial time algorithms if m is less than n to the k over 2. And so what I want to tell you today is the story on the right-hand side, all the story in green. And so, the question of algorithms or like trying to find refutations efficiently, I think, again, has like a long history. And I'll just maybe tell you like a few important milestones. So there's like a non-trivial refutation that, you can do using resolution proof systems, and you can even find such proofs efficiently. And that was shown in this paper of Tony. In fact, it's the same paper that proved the lower bound I mentioned earlier. So this was like a non-trivial density below n to the k, but it did not achieve the n to the k over 2 density. And that required the introduction of this cool new idea of having a spectral refutation. Okay, and this is somehow what I'm going to tell you about a little bit more. And so it began in this paper of Girth and Krivlevich, which is really very influential. And somehow one of the aspects of this line of work is that somehow even arity behaves very differently from odd arity. So, the Girth-Krivlevich method was like very reasonable, very nice heuristic for even k, but somehow it didn't even make sense for odd k. So it took a while to get the correct analog for odd k, and then the analysis took somewhat more time. And it was eventually done for k equals 3 and 4 by Koja, Oglan, Gert, and Lanka, and then, generalized to higher k in like, some newer papers. The upshot of all these works is that, we now have a polynomial time refutation algorithm whenever m is bigger than n to the k over 2, and I'm ignoring polylog factors. One key important fact is that, when we think of resolution, it somehow naturally only weakly refutes a formula, but the spectral refutation would end up not only weakly refuting, but in fact, strongly refuting the formula. Okay, and so this is something that we really like, from my perspective, so we'll focus on. Okay, very good. So because this number n to the k over 2 turns out to be like the breakpoint of natural algorithms, and there are lower bounds that kind of rule out at least some restricted class of proofs below this threshold, it goes by the name of spectral threshold. At least that's what I'll call it in this talk. Okay, very good. So I want to tell you a little bit about this spectral refutation, so that you have an idea and you see how simple really it is. And I'll take the example of random 4 XOR. And the 4 is basically the simplest non-trivial even number here. So, that's the reason I'm looking at 4 XOR. I'm looking at random because, that's particularly easy. I'm looking at XOR because it turns out that, XOR has all the complexity of SAT and other CSPs, but somehow is easiest to think about in this context. Okay. So what does XOR mean? Just in case, you've forgotten about it. XOR is simply, the CSP where the constraints are on 4 tuples, and they say that, the XOR of the 4 bit should be 0 or 1. I'm going to look at it in the ±1 world because it somehow serves my agenda a little bit better. So, I'm going to think of like the assignments to take values in ± 1. And in this world, 4 XOR constraint simply, means that the monomial of 4 bits, like the product of the 4 bits, is ± 1, according to whether it is supposed to be 0 or 1 in the usual world. Okay. All right. So how do you, use spectral methods to refute such a formula? Well, we'll think of an instance as described to us by like a 4 uniform hypergraph, and the right-hand side is BC. So, the 4 tuples that appear are described by the hypergraph, and, the right-hand sides by the B sub Cs. And given such a formula, given such a 4 XOR formula, I'm going to think of the following homogeneous degree 4 polynomial. Okay. So what's this polynomial? it basically, has one monomial for every constraint in my XOR system. Okay. So if you look at, each term here, it looks like the product of the corresponding right-hand side with the monomial, describing the 4 XOR constraint. And the key thing to observe is that, if a certain assignment X satisfies that constraint, then this monomial evaluates to +1 because, B sub C and the monomial will have the same value, +1 or -1, right? And so, as you can see, for every satisfied constraint for a given X, you gain a +1, and for every unsatisfied constraint, you gain a -1. So because I've normalized by the number of constraints, you can easily see that this polynomial simply computes the advantage over half, the normalized advantage over half, that an assignment X can get you. Okay. Again, feel free to stop me if any of this is unclear, because I really hope that I can convey the sense of how simple and easy this stuff is. So very good. Okay, so therefore the task of refuting, or at least strongly refuting, simply reduces to proving or finding a proof that this polynomial is never larger than some tiny number, let's say epsilon, for every possible X in ±1 to the n. Okay, so how am I going to do this spectrally? Well, here's how. Okay, I'm simply going to write, and this is the key idea of girth and privilege, by the way, to write phi x as a quadratic form of some fixed matrix. Okay, and I'll tell you what this matrix is because it is so simple. This matrix is indexed by pairs of variables on rows and columns. Okay, so let's say ij on the rows, k sub l, k and l on the columns. So there are like n choose 2 rows and n choose 2 columns. The ij k lth entry of this matrix equals the right-hand side of the constraint xi, xj, xk, xl equals ±1 if such a constraint exists. Otherwise, it is 0. So in particular, the entries of this matrix are just 0, +1, or -1. Okay, that's it. That's the matrix. Once you know this matrix, I can tell you why phi x is a quadratic form. It's like really simple. I'll tell you the vector over which, if you take the quadratic form of this matrix, you actually get the formula phi x. Why is that? So just take the following vector. I'm going to write x circle 2 for the n choose 2 dimensional vector that simply computes the homogeneous degree 2 monomials in X. So like the ijth entry of this vector would be xi times xj. So I'm using circle because it's kind of like X outer product with itself, or X tensor to the 2, but not quite, because I only want to keep n choose 2 monomials. So I'm just inventing this notation of circle. It's not standard, but I hope you follow. So given this vector of monomials, it's actually very, very easy to verify that phi x is simply the quadratic form of this matrix A on X circle 2. And because for a given ijkl, there are like 6 different ways it can arise, I'm just scaling it down by 1/6. That's it. Okay. So once you agree, and don't worry about too much about like the number 6 and like making sure that it's correct. As long as you agree roughly that this kind of makes sense, observe that we arrive at a very simple way to upper bound phi x. Namely, any quadratic form can be upper bounded by the L2 square norm of the vector times the largest singular value of the matrix. That's exactly what this inequality says. And the key thing is that this expression is independent of X. Why is that? Well, because X circle 2 has entries which are ± 1. So the L2 square norm of this vector, no matter what X it is simply n choose 2. Okay. So this right-hand side is simply 1/6 times n choose 2 times the singular value of A, the maximum possible singular value of A. So all we need to understand, if we have to get a refutation, is simply to understand what this largest possible singular value is of this matrix. Okay, and when is it small enough that we get a refutation? So really, like any reasonable technique to bound this eigenvalue works. The key observation is that A is roughly a random matrix. Sorry, A is roughly a random matrix because its entries up to these permutations, like 6 different permutations, are simply independent random, because bijkls were independent random. And so for such random matrices, you can use basically one of the many techniques we have to prove bounds on singular values. And you can show that this succeeds in refuting random 4 XOR instances as long as they have at least n square clauses. Okay, that's it. Now you know the girth privilege idea, in case you did not know that before. And so let's move on. Which is, to ask the same question about 3 XOR. Okay. And it's actually kind of amazing what stops us. What stops us, was observed by this famous proof complexity theorist 150, or in 150 years after 0, where he said, that rectangle is not a square. Okay. I'm not sure that this is a quote by him. This is simply my guess for what he would have said to our problem. And the problem is that there is no square matrix of which a quadratic form phi x appears to be. It's like phi x is a cubic polynomial, and we simply don't know how to write it as like a quadratic form. That's it. That's our problem, and that's basically everybody's problem. Okay, so it's not like we are stopped by this. We work a little bit harder. Turns out that you can write a different matrix. It's slightly more complicated, so I won't write it down. But it's an n square by n square matrix. Okay, it's a square matrix, and it kind of corresponds to writing down the matrix for a different polynomial. So you start with phi x, but you construct like a degree 4 polynomial from this cubic by doing one step of Cauchy-Schwarz. If those words mean something to you, that's fine. If not, ignore. But there is a certain matrix you can write down. What actually happens though is that because just some basic math, basic amount of randomness being different because of this like dimensions changing, it turns out that the entries of this matrix are no longer independent. They in fact have like much stronger correlations than before. So we can't quite analyze the eigenvalues of this matrix as easily as we did in the previous slide. We can do it, but it requires bringing out some big guns. It needs this so-called trace moment method, which requires some sophisticated combinatorics to completely work out the bounds, and somehow needs to strongly use the randomness in both the clause structure and the right-hand sides. Okay. And so that's my, accurate depiction of how the trace moment method looks like. It's basically, some heavy duty method that one has to use in this context. Good. So that's all great. But we don't like this scenario because, because it somehow uses this somewhat, combinatorics heavy method. It does not make it clear where the randomness of the clauses is getting used and where the randomness of the right-hand sides is getting used. And it does not reveal to us, where somehow these assumptions are playing a role, and in particular, how to remove them, right? So, this remained like a kind of a big challenge for a while. And there was like a progress made by Feige about 15 years ago when he found some hack to actually get weak refutation for random 3-sat formulas. Actually, this worked for the smooth model I did not tell you about. So think of this as semi-random right now, okay? My bad for not removing the word, but he basically found a way to do weak refutation for semi-random 3-sat formulas, by somehow combining spectral methods with a combinatorial trick, which I'll hopefully get to. But somehow, this is such a hack that it does not extend beyond 3 CSPs, and it certainly does not get you strong refutation. So, we were kind of stuck here. And, like a few years ago, maybe a couple of years ago, we actually figured out like the right answer here. We basically figured out like a polynomial time strong refutation algorithm for semi-random k XOR for all k. In particular, the odd k was the more challenging part at the right density. And the key thing is the main message of the talk, which is that somehow we found like a new method to analyze the random case. And somehow the nice thing is that this new analysis is still a spectral method, but it does not need trace moment method. Instead, it simply relies on a correct application of off-the-shelf matrix concentration inequalities. And once you do that, it turns out that you can lift it up using some of squares proofs or SDPs, which I'm not going to tell you about, to the semi-random setting. This is in fact, again, some another basic principle, which is that if you have like a proof that uses the right spectral method for the random case, then a certain semi-definite version of it usually would work for the setting with like less randomness. Somehow SDPs are slightly more clever than spectral methods, and so they somehow extend to semi-random setting, even though the spectral methods won't. But I won't tell you about that. Instead, I will move on to this story that we were looking at. So I told you a little bit about this right-hand side, the right-hand side to enter the k/2 threshold. But let's come back to the left-hand side again. We said that there are no polynomial time refutation algorithms, at least in this basic proof systems. But it still doesn't rule out the possibility of beating brute force. Like, can we still get like sub-exponential algorithms? And I'll tell you a little bit about how we can and what happens. But towards the end of the talk, I'll show you this. Even if like the search for sub-exponential proofs and sub-exponential refutations like kind of bothers you, like why are we looking at these kind of big bounds? You'll soon see that somehow it relates to polynomial size refutations in a very interesting way. So there is good reason to care about them, even if you only think that polynomial size proofs count. Okay, so the result here was first proven by Raghavendra Rao and Shram, again like 6 or so years ago. And what they proved is the following trade-off. Okay, they proved that for every number L, there is a n to the L time algorithm that succeeds in refuting, random k-set or random k XOR formulas, as long as they have the following number of constraints. And, I like to read this bound as the way I've written it. It's like n times n over L to the k over 2 minus 1. Why do I write it like this? Well, because, if you set L to be 1, okay, that's like, polynomial time algorithm, the bound becomes n to the k over 2. While if L is set to n, the second term disappears and the bound becomes n. So in some sense, you can think of this as, interpolating in the exponent, of the running time, and like increasing the as the the density increases from like n to n to the k over 2. So if you draw the constraints in log scale, then my line is indeed straight as I've drawn on this slide, the yellow line. Good. So that's the result I want to tell you a little bit about now. As usual, we start with the same 4 XOR example we were looking at earlier, but this time, we are trying to upper bound the polynomial even when we have much fewer number of constraints. So like, let's say in this trade-off case, we have like n square over L constraints, and think of L as like something growing. So like, n to the epsilon, okay? Good. So, this was first done by RRS, the paper I just told you about. They use like a matrix, which, let's just for whatever, for the sake of having a name, let's call it symmetrized tensor power matrix, which has some motivations, but let's not go into it. Our issue is the same with it though, which is that, it's like even more technical in application of the trace moment method than like the previous example I showed you. So it kind of even more makes it harder to disentangle where the randomness of the graph is being used, coupled with the randomness of the right-hand sides. So we are again in trouble, and actually a somewhat bigger one here compared to the previous slides. And so, people realize this. So, there were like multiple attempts to try to simplify their proof. In particular, the idea of Wine, Alaoui, and Moore is particularly influential, and I want to talk about that right now. So what these two papers managed to do is like, try to find like a simpler proof for random 4 XOR refutation. And somehow, their stuff really restricts to even. Again, like, the same curse of even versus odd strikes us. So, this Wine, Alaoui, Moore idea works for even arity random k XOR, somehow doesn't work for, beyond random or odd arity XOR. In fact, they suggested a construction, but it turns out that the construction's claim is simply false in the sense that, there is no in fact, there is no analog of their idea that somehow gives a spectral refutation, it turns out. I'll soon show you how to like fix it, okay? But because the idea is so neat, I'm going to tell you about it, okay? I can again write it down completely in a slide. So what's the idea? The idea is again to write phi x as a quadratic form, okay? But this time I'm going to write it as a quadratic form of a huge matrix. For this parameter L, I'm going to construct an n choose L by n choose L matrix, okay? You can almost see by the dimensions of the matrix what the rows and columns should be. They should clearly be subsets of variables of size L, okay? And what entries should they have? Well, I'm going to have an entry of B sub C if the symmetric difference of the row and column indexing subsets happens to be a 4 size set, a 4 tuple, which corresponds to a constraint, okay? Otherwise, it's going to be 0, okay? So this is my matrix A sub C. It's like, for a single constraint appearing in my 4 XOR system, I'm going to have this matrix. And basically, I'm going to have an entry non-zero for every pair ST which XOR out to C, or which like simdiff out to C, okay? Notice that, this is a pretty sparse matrix because, an entry requires that S and T have like a symmetric difference of 4, even though they are both sets of size L, okay? But we're okay with that. We don't mind, okay? So that's A sub C. What's the matrix, of which phi x is a quadratic form? It's simply the sum of A sub C's as C varies over all possible constraints. Okay, good. So I'm not gonna, suggest that you try to read this expression, but look at the length of it to convince yourself that there is a very short proof that convinces you that phi x is indeed the quadratic form of this matrix. Okay, so don't read it. Just be convinced that it's a small proof. That's great because, all we need to do again is to, upper bound the largest singular value of this matrix A in order to get a refutation. Okay. And the idea is very, very simple why this is going to work out. And the reason is, the way I wrote A already. So A was a sum of matrices. And actually when C are random and the right-hand sides are random, it's a sum of independent random matrices. So what I have is like a sum of independent random matrices. And so I can apply, off-the-shelf matrix concentration inequalities that work for, sums of random matrices. And if you just like plug in the right inequalities, you get the right trade-off for refutation that you wanted. That's it. Okay. So that's great. But, we are in the same situation. What do we do for oddality? What do we do for semi-random? And again, we've got to somehow find the right proof. And actually, that we happen to do just very recently. So we actually found like a variant of this Kikuchi-like matrix, the one I showed you on the previous slide. Again, not going to write it down for you. I'm going to call it the pruned spectral norm because it's like it's not a spectral norm actually. It's, something that can be computed easily using a semidefinite program. It looks like spectral norm, but it's not quite. But it turns out that, that kind of, norm actually works with the simple matrix that I looked at, or some natural variant of the simple matrix I defined in the previous slide. It does work even for odd K. And then, you should ask what happens when I try to generalize it beyond random. It also works out, slightly more effort, but works out anyway. But it needs some like cool new tricks. So, we prove like a new hypergraph regularity lemma to somehow, go with it. And, it turns out that if you have the right regularity lemma and this pruned spectral norm, you can somehow piece them together, into an analysis of some nice simple SDP that does give us the exact right trade-off, even for semi-random setting. Good. That's all I have to show you. Okay. Like, I wish I could tell you this proof, but, I won't. So the last part of my talk, how much time do I have, Robert?
Like 6 to 8 minutes, because we started a little bit late.
Okay, very good. Yeah, that's exactly the amount of time I need. So, I told you 2 techniques to refute random CSPs and semi-random CSPs so far. I told you about spectral techniques and how somehow, if you have to reduce randomness, you can like upgrade the spectral method to SDPs. Now I want to tell you the third technique, okay? And that's this idea of even covers, and I'll soon tell you what those are. It was introduced, in the context of finding refutations for random 3-sat. And here is the very curious result that Feige, Kim, and Ofek proved in 2006. So, so far we have been treating n to the k over 2 as a spectral threshold. And we've been thinking that, there are no short proofs below n to the k over 2. Well, to be accurate, we don't know of any algorithm to find short proofs below n to the k over 2. But, in this really clever, weird paper of FKO, they managed to find like a weird phenomenon where there actually is a short proof significantly below n to the k over 2. Okay. So in particular, they showed that there is some fixed constant depending only on k, such that at density n to the k over 2 minus delta k, so like strictly polynomially below the spectral threshold, there is in fact a polynomial size weak refutation, for random 3-sat. And they did this by this, clever combinatorial construction of even covers that I'm going to show you. So in particular, the number you might want to keep in mind is like for 3-sat, this density happens to be n to the 1.4, okay, which is like, n to the 0.1 short of this spectral threshold of n to the 1.5. Good. So, but before I tell you all of that, the same spiel applies, which is that, it turns out that if you get the right proof of FKO that does not utilize randomness too much, then, you actually get a generalization. So, we basically find like in some sense a simpler, in my opinion, slightly simpler proof of FKO. And because, we are able to do that, we are actually able to generalize it to, the semi-random setting. And the key thing, which is what I'll tell you in the remaining 3 or 4 minutes, is resolving this very simple, completely standalone extremal combinatorial conjecture of Feige from 2008. Okay. And because this is so cute by itself, I'll tell you essentially only about this and only hint at how it relates to refutation. Okay. Good. So if you were, bored or, distracted so far, you can come back because this is completely standalone. Okay. So here's a question I'll ask you. Suppose I give you a graph on n vertices. So before hypergraphs, let's look at graphs. Suppose I give you a graph on n vertices, which has like average degree d. So in other words, it has like n times d over 2 edges. The question is, how large can you make the length of the smallest cycle? So how large can you make the girth of this graph if you are restricted to have at least n to the n times d over 2 edges? Okay. So if d equals 2, then I have n edges. I can certainly take like one giant cycle and that would be a, girth of n. But it turns out that if you make the average degree even a little bit larger than 2, there is a log length cycle in the graph. So there's like a sharp drop from n to log n. So in particular, here is a famous theorem of Noga alone, Huri and Lineal from 2002, which goes by the name of irregular Moore bound. And they prove that, if the graph has average degree d, then it always has a cycle of length 2 times log n to the base d minus 1, plus some additive number. Turns out, this constant in front of the log term is actually, subject of intense research. We know that 4/3 is necessary. We don't know if we can reduce it below 2. And, the tight examples happen to be the Ramanujan families, but, not our concern today. I want to talk about a similar conjecture for, hypergraphs. Okay. And this is the conjecture that Feige made. So, I have to tell you what a hypergraph cycle is. So cycle in a graph was a subgraph that, you can think of as a subgraph that touches every vertex an even number of times. Okay. Really, if you take like such a graph, it's a union of cycles. But the only property I want to remember of a cycle is that, every vertex happens like, an even number of times in it. Okay. If you think of this property and generalize it, you get the definition of, cycles in a hypergraph. So a hypergraph cycle is simply a collection of hyperedges or a sub-hypergraph which touches every vertex an even number of times. Okay. Now, why should this matter to us? Basically, a even sub-hypergraph, if you think of each hypergraph, each hyperedge as defining, the non-zero coefficient, variables in an equation, so a k sparse linear equation, then a sub-hypergraph, which is even, is simply a linearly dependent subset modulo 2. Okay, so you can see why, in some sense, XOR-like structure is appearing, and that's roughly the level I'll stick to at the moment. So, this happens to be the size of the smallest linearly dependent subset of k sparse linear equations modulo 2. And so, here is what Feige conjectured about it. It's basically the analog of the irregular Moore bound I showed you for graphs. He said that, if you have a hypergraph which for parameter L happens to have n times n over L to the k over 2 minus 1 edges, this is the same kind of thing that you saw earlier, and, for good reason. Then he claimed that it must have a cycle of length L log n. Okay. Again, the extremes are, pedagogically nice. So if you think of L equals 1, then this is saying that, at n to the k over 2 hyperedges, the hypergraph should have like a log length cycle. So it's a little bit like, if k is 2, then that's n. So that's like the setting for graphs. Okay. But turns out for hypergraphs, non-trivial things happen, even below this threshold. And so, for L, which is like n to the epsilon, there is some strictly, you can have an n to the epsilon then cycle, even when the number of hyperedges is like, way short of n to the k over 2. Well, that's what Feige conjectured. And, it has like nice coding theoretic interpretations, etc. And, his reason was that, random hypergraphs actually achieve it. So, he checked that random hypergraphs satisfy this property, but he thought that, this should be true for all hypergraphs, like worst case. So, so that's what he conjectured. And maybe like, I don't know if it's easy to digest, but it turns out that, if you have one such cycle of length L log n, then just like, removing the hyperedges appearing in it and repeating shows you that, you can construct many such cycles. And so it turns out this fact is somehow important in refutation applications. And, he used this fact somehow to get this FKO result I mentioned earlier. So this was somehow the key idea. And he was able to prove this consequence directly by analyzing, random hypergraphs. And he used the second moment method argument. So this was what I was telling you, what he was able to use the randomness of hypergraphs to prove. But, he really thought that this should be true for all hypergraphs, and that was a conjecture. So, there were like multiple attempts over the years to try to prove it, but basically, it was kind of open at all but the extreme points. And the upshot is that, we can actually prove that conjecture in full. The conjecture is true. And, proving that conjecture immediately basically extends this FKO result to all hypergraphs and therefore, to the semi-random setting. And so the only thing I want to tell you, the very last thing I want to tell you is how the proof works. Okay. And this is like the payoff I was telling you that you would have if you actually study sub-exponential time refutations. So our proof really works the following way. We show that suppose for the sake of contradiction, there was no such cycle, no small cycle as Feige's conjecture suggests, then there should not be any sub-exponential size spectral refutations for semi-random KXOR. But because we just proved they exist, there should be hypergraph cycles. This looks like an absurd way to prove it, but actually, trust me, this is how we discovered it, and this is how it actually works. So, that's some payoff for studying sub-exponential size refutations if you needed some. All right, so that's basically it. This is like the gist of the talk. Somehow everything that we know for random actually succeeds for smoothed and like semi-random settings. I told you, like, if spectral works for random, then somehow SDP can be made to work for semi-random. Spectral succeeds somehow, only when these even covers or hypergraph cycles exist. And, maybe the true wisdom is, what this other proof complexity theorist said long time ago, maybe, which is to look at these, Kikuchi matrices, this weird, symmetric difference matrix that I defined earlier. All right, so, I'll let the open question to appear in like Susanna's talk, and that's all I have. I'm sorry, I maybe went over like a couple of minutes.
Don't worry. Okay, so for the last part of our workshop, Susanna's, we've collected a lot of open problems from all the speakers, and Susanna's going to kind of give a nice overview of future directions. So take it away.
Yeah, great, thanks. Yeah, so these are several open problems. Many of them appeared in previous talks, so I won't get into a lot of details because there's no time, but you can go back to the talks and take a look at them. Let's start with the origin of proof complexity. Is there a polynomially bounded proof system, right? So here we have a sequence of like proof systems, stronger proofs, which green can and Feige. So in the proof on the floor about unless
No, yeah, okay. Susanna, I'm not sure if you can hear us, but you're breaking up a bit.
okay. Oh.
He's back.
But I'm gonna connect the data just in case. I don't know what.
Okay.
Okay, are we back?
Yep, I think
Okay.
we're back. Okay.
Okay, good. Yeah, hopefully this will be stable. Right, so if that's a second important question, is there an optimal proof system? Right. So if there's an optimal proof system, we only have to prove a lower bound for that. And this is, as Krychek mentioned, this is related to many different topics, and you can look at his book. He has a chapter only on this. Okay, so going into proving lower bounds for these strong proof systems. So an important question is, can we prove super polynomial lower bounds for these? And there are some easier questions that we can address. For example, can we prove conditional lower bounds using a conjecture that doesn't make the problem trivial, so that doesn't imply NP is not equal to CONP? Or even like, can we prove superlinear lower bounds for CNF formula? So even this we cannot prove for these strong proof systems, or super quadratic for any formula. And we can also consider like subsystems of like weaker proof systems. So for example, a subsystem of AC0 to Frege would be res parity. And even for this much simpler proof system, we don't know how to prove super polynomial lower bounds. Then another very interesting open problem is to prove exponential separations between depth D and depth D plus 1 Frege for KCNFs. And like initial case one could address is like separating res log from AC0 Frege. And there are analogous questions in bounded arithmetic, which Neil mentioned in his talk. Okay. Then we also saw algebraic proof systems. So we in the beginning talked a lot about the ideal proof system, So just to remind us, so we have here I'm describing like Nullstudent sets. I have a set of polynomials, and the Nullstudent set of refutation of this set of polynomials is another sequence of polynomials such that when I sum the product of these, I get the syntactically 1. And the IPS is simply a circuit that is encoding the Nullstudent set refutation. So yeah, as Tony and Josh said in their talks, so an open problem is to prove lower bounds for IPS for CNF formulas, even for restrictions of IPS. There was this exciting new result just very recently, which proves super polynomial lower bounds for constant depth IPS, but they use the input polynomials that are not constant depth. So it would be good to improve this for input polynomials that have constant depth. And then there's the question of whether extended Feige can simulate IPS, which is related to the question of what is the proof complexity of polynomial identity testing. Okay, so this is for algebraic proof complexity. Then we have monotone protocols. So I'm not going to get into details here because it would take, I think, a bit too much time. But the idea is that monotone protocols can be, we can represent them as some DAG, which every node in the DAG is related to some communication problem. And these DAGs, they correspond to different circuit models, or depending on what the problem we're solving corresponds to, can capture different proof systems. So there's this question of proving super polynomial lower bounds for monotone protocols solving the monotone KW relation, where the related communication model allows for 2 rounds of real communication. So this is a communication model. If you've heard of it, you can also think of it as intersection of 2 combinatorial triangles. But the idea is that we know how to prove lower bounds if we only allow 1 round of real communication per node. And this gives lower bounds for example, the cutting planes proof system. But if we allow 2 rounds, we can't prove lower bounds. And if we could, we would get lower bounds for the rest parity proof system. Okay. Then we had 3 talks about the TF&P. So in Neil's talk, there was, yeah, it was Neil's or Sam's talk. We had this question of, can we have, so here I wrote like a sequence of the different TF&P classes, and we have the GI classes, these game induction principles, I think they're called. And we know that GI1 is equivalent to PLS. GI2 is equivalent to this CPLS. So there's this question of whether we can find simpler or more combinatorial equivalent classes for higher GIKs in the sequence here. And also to prove relativized separation between different levels of this hierarchy here. And this is morally equivalent to the question we saw earlier of proving, well, better than quasi-polynomial separation between depth D and depth D plus 1 Feige for KCNFs. Okay, now like restricting ourselves more to this lower part of the TF&P classes, we have a relation that looks like this. And as Robert showed us in his talk earlier today, these classes have all some relations to different proof systems. So this PLS, which is related to resolution. We have a FP, which is related to tree-like resolution. And then there are other like Nullstellensatz sets, unary Nullstellensatz sets, that's like Nullstellensatz sets with low coefficients, F-Shirelli-Adams with low coefficients, and max-sat resolution. And similarly for circuits, there are also models which are related to these TF&P classes. So here we have like several interesting open problems too. So like, can we complete the picture like with regards to separations, with regards to these relations? There are several open problems there. Also, as Robert mentioned, we have like other intersection results, like he mentioned that this recent work shows that max-sat resolution is actually equal to resolution in low width and unary Shirelli-Adams in low degree, the intersection of these. So are there other such intersection results? And yeah, another question is, so the relations between these proof complexity and circuit complexity results in one direction go through these lifting theorems, but the circuit lower bounds are for monotone. So can we use the same kind of like lifting for some kind of non-monotone circuit lower bound? And then regarding these relations to proof complexity, there are some proof systems for which we do not know how to capture them in TF&P. So for example, sum of squares, and also the IPS proof system can, perhaps might be a class even beyond TF&P, since we don't know how to de-randomize polynomial identity testing. Perhaps beyond TF&P, we can have a class that captures IPS. There are also others that seem hard to characterize within TF&P, like cutting planes or Lovo-Shriver. And yeah, so these are some of the open questions here. Then we also heard of many like interesting formulas. So for example, we just talked a lot about random KCNFs, and there's proof systems for which we do not know how to prove lower bounds. So for constant K, we don't know how to prove lower bounds in cutting planes or AC0 Frege. Then there are other like combinatorial formulas which are interesting, for which we don't have too many results, like coloring or Ramsey theorem. Then weak pigeonhole principle. We know that AC0 Frege, we have a quasi-polynomial upper bound, but we don't have any lower bound there. So does the AC0 Frege have polynomial size proofs of weak pigeonhole principle? And even other proof systems like polynomial calculus, we only have degree lower bounds, but we don't have polynomial size lower bounds for weak pigeonhole principle. Then other proof systems, other formulas we've heard about also a lot, like these proof complexity generators, like Nielsen-Wigderson generator, Krychek's Gadget generator, or these truth table generators are formulas that are conjectured to be hard. And for like stronger proof systems, we don't know how to prove this. And also the reflection principle, which, yeah, we also heard a lot about in Rahul's talk. Okay. Then there's several other complexity measures other than size. So we have width, degree, or depth or space of proof. And an interesting question is to understand if these are like polynomially equivalent. So there have been some results in this direction, but there's still like open problems. And we did not talk about this during this workshop, but Razbarov and Papamakarios have a paper where you can see some more open problems on this. Also, trade-offs, something we didn't talk about here, but they're understanding what happens when we try to minimize these measures if we can minimize them simultaneously, or whether we get some kind of trade-offs. And I think two very interesting questions here are, whether there exist formulas such that if we want a minimal size proof, it must have superlinear depth. So in particular for like cutting planes, and a very well, a candidate formula would be Satan. So Satan was conjectured to be hard for cutting planes for several years, but recently there has been a quasi-polynomial upper bound shown. But this quasi-polynomial upper bound also has quasi-polynomial depth. So is it the case that any minimal size proof, any quasi-polynomial size proof of Satan does actually require superlinear depth? So yeah, this is not known. And a similar question for circuits can be asked. So are there functions that if we want minimal size circuits, then it will require superlinear depth? So for example, matching might be such a function. We only have a quasi-polynomial lower bound. Could it be that there is a quasi-polynomial upper bound, but it also requires quasi-polynomial depth? So yes. Okay, and then we earlier today talked about proof search, and so there's with regard to proof search, we can talk about automatability, which has to do with this second question of if a tautology admits a small proof, can we find it in polynomial time? So a proof system is said to be automatable if this is the case, and there are several proof systems for which we don't know how to prove that it's non-automatable, assuming P is not equal to NP, like sum of squares or bounded depth Feige. And then there's the notion of weak automatability, which is very similar to automatability, but the algorithm is allowed to output any proof of the tautology, not necessarily, it doesn't have to be a P proof. And the big question here is whether resolution is weakly automatable. Okay, and then I'll just go quickly over the next two slides because we just saw it today. So Krychek talked about this other view of proof search, which is more information theoretic. And basically, the question is still, is there an optimal way to search for proofs? And this information measure, it really like captures the best algorithm for a given proof system. So we have a lower bound of 2 to the information measure for any algorithm that outputs P proofs, and there is an algorithm that actually up to polynomial factors matches this lower bound. Well, clearly the size of a proof is a lower bound on time, and consequently on this information measure. But another way to prove a lower bound on the time required would be to prove a lower bound on information. So what Krychek was asking is, if we consider a proof system P for which we cannot prove size lower bounds, we still don't know how to prove it, can we obtain information lower bounds, which would give time lower bounds for algorithms outputting these P proofs? So we can also state this as, is it easier to prove lower bounds for information than for? Okay. And finally, earlier in the session, we had talked about meta complexity. So why is it so hard to prove lower bounds? In particular, like even Feige or extended Feige lower bounds. So can we show that there is some distribution of formulas which are believed to be hard for extended Frege, but are somehow hard to prove? So under some conjecture, sampling some formula from this distribution with high probability, extended Frege cannot prove a super polynomial extended Frege size lower bound for these formulas. So formulas that we believe to be hard, but we can show that they're actually hard to prove under some conjecture. And also Rahul talked about, can we show that Bus's theory, S12, cannot prove that NP is average case hard for CONP/poly. And then this more classical question of whether we can show that a proof system P cannot prove that SAT is not in P-poly. And this is known for resolution, low degree polynomial calculus, but not for stronger proof systems. And finally, I have Pravesh's last open problem, but I don't know if actually you want to talk about it.
You're muted.
Sorry, can you hear me now?
Yes.
Yeah, it's my favorite open question. It relates to whether actually this n to the k over 2 is a threshold we should be scared of at all. And so this open problem basically is saying that maybe it isn't. So the question asks you to find an algorithm to basically refute a random 3-sat formula with like slightly lower than n to the 1.5 constraints. Okay, so the number of logs there is not important. Basically, add as many as you want, but basically find a polynomial time algorithm to refute a random 3-sat formula. A weak refutation is fine with that many constraints. Now, this might look like a terrible way to ask a problem. It's like, I'm just telling you, find such a thing. But there is a reason to believe this might be possible. And that's because, the refutation actually could consist of this even covers, like the stuff I was talking about, the hypergraph cycles. And so, there are algorithms based on color coding and whatnot for finding like cycles of log n length in graphs. And so the question is like, is there a similar algorithm for finding this hypergraph cycles? So again, even this formulation has been studied, I think in the past, but this new work that we have relates this hypergraph cycles to, actually cycles in some other graphs. So they actually make it somewhat more tractable. And so like somehow I kind of feel like, maybe there is a shot that this problem might now fall, which would be great because, maybe at the end of it, we'll learn that n to the 1.5 was not a threshold at all. Maybe there are like algorithms that work beneath it. Yeah, but that's it.